So here we have an ester, and it's reacting with lithium aluminum D4. What the heck's D4? What's D? D is actually deuterium, that's right. And so it's really just, we call it heavy hydrogen, right? Hydrogen with an extra neutron. And we use it in NMR studies because it's not NMR active. And so it's a way for us to see where things are reacting, right? So if this molecule has a D and that doesn't show up in the NMR, that tells us something about where things are reacting, right? So it helps us understand things. That's why we use deuterium a lot of times. Otherwise, the mechanism is exactly the same, right? So the only change here is that we're just using D. So we do that addition. I'm doing it fast. You of course would number everything. Elimination. Gets us to a aldehyde type intermediate. Right, D is not H, but like it. Balance that charge there. Another D minus would come along. This is exactly what I'd want you to do if there's versus or H minus, same idea. It adds in addition. You get a tetrahedral intermediate. This time there's no good leaving groups. So what are you going to do? You're going to do the final step, which would be protonation, which I don't necessarily need to show here. You get a primary alcohol in this case. So here we have lithium aluminum hydride, which we know is the more reactive form of hydride. So we know before I even look at what it's going to, I'm just thinking in my head. I see lithium aluminum hydride, and I think of this, and I say, lithium aluminum hydride will react with ketones, aldehydes, esters, amides, and carboxylic acids. I know that in my head. And then I look at the molecule and I say, what does this molecule have? It has an alcohol, a ketone, and an ester. Esters in the ring are called lactones, if you didn't know that. So you have an ester, a ketone, and an alcohol. Hydrides react with carbonyls, C double bond O's. So I'm looking right there right away. It says it's an excess, so I know I'm going to have a lot of H minuses, essentially, right? I can have as many H minuses as I want to make this reaction go. So if I was going to draw the mechanism of this, I drew some numbers already. What's more reactive, the ketone or the ester? The ketone, right? Because the ester can do resonance, which makes the carbon of the carbonyl group less delta plus, less electrophilic. So let's have that one react first. All right, we do that addition step. We did that addition. We get a tetrahedral intermediate. We ask ourselves, does this tetrahedral intermediate have any good leaving groups? It does not. So then we immediately go to protonation, but we stop because we're not quite there yet. We still have to have the ester react first. So you can't, right? Don't go mixing steps. You still got H minus floating around. We still need to react the ester. So you're just going to have that O minus just, it's hanging out. We're in basic conditions. It's just going to be there. It's okay. So we have another H minus come in. We do another addition. Did that other addition. Now we have a tetrahedral intermediate. If we have a tetrahedral intermediate, what do we ask ourselves? Do we have a good leaving group? Do you have a good leaving group? All right. By God, you do. Electrons come down. We do that elimination. And we lose that leaving group, elimination. What's going to result now from this? So now from this, we did that elimination. We got another O minus. Now we have an aldehyde. Guess what? We started with the ketone and ester. Ketone reacted first because it's more reactive. Then we reacted with the ester. And along the way, we made an aldehyde, which is the most reactive. So now we're going to have another H minus add in. Right? Once again. So after that third addition now of hydride, we've added 3 H's along the way. 1 for the ketone and 2 for the ester. Now we got 3 O minuses. Whatever, it's fine, right? We're in basic conditions here, right? We're in basic conditions here. So that's all good. Now we just do protonation. And a lot of times what happens here, it doesn't say this, but when you see H+, you can assume excess, right? It's going to protonate all of them. It's going to protonate all of them. You can do it all in one step if you want to. You go, H+ for everybody. Going to need at least 3. Everybody, you get an H+. You get an H+. You get an H+. It's like Oprah and Cars. Everyone gets an H+. So then we have the final product, and that final product is this tetraol. Tetraol, and the numbered atoms as you go. Numbering system always really helps. But again, do these kind of problems and then go looking for the answers, especially on multiple choice ones. So this is kind of nice because this kind of combines a couple of things, right? You've learned about ketones, you've learned about esters, but can you do a molecule with a ketone and an ester? What's that going to look like? Things to remember, you have lots of H minuses. Just draw it as H minus. If you see H+, assume it's an excess. You'd protonate everything. You assume it's an excess, you'd protonate everything. Epoxide. Epoxide, reacting with a grignard. Couple things to be aware of. When you have a grignard or a hydride or things like that, things with a negative charge to carbon or hydrogen, that's considered basic conditions. Now somebody's going to say, well, wait a second. There's H+ right there. Yes. That's why we have these numbers. That's why it's really important to say number 1, number 2. So when I say basic conditions, I just mean the step that involves the epoxide. Right? Then we use acid at the end to do protonation. But I consider this basic conditions. If the acid was there first, then it's acidic conditions. But then I couldn't have a grignard, right? Because grignards can't have polar protic or H+ around, right? Because grignards are going to react with that. So, basic conditions. When I have basic conditions, the most important thing here is actually thinking about sterics, right? Sterics. So, which carbon is less sterically hindered? Carbon 4 or carbon 5? Carbon 4 is less substituted. That means it's less sterically hindered. This is like an SN2 reaction. You did this with bromonium ions, right? There's something very similar with bromonium ions, right? So this is just an SN2, like a substitution reaction, right? There's eliminations, substitutions, additions, protonations, deprotonations. There's not that many reactions, so substitution. Tricky part here, make sure you number your atoms because you don't want to lose things. Classic things people do, they'll lose carbon 1 all of a sudden. Carbon 1 will just become part of carbon 4 somehow, right? Don't do that. Be careful, right? So there's carbon 1. That means this is carbon 4. What else is carbon 4 bonded to? Well, it was bonded to oxygen. It's not bonded to oxygen anymore, is it? The oxygen, O6, is still bonded to 5, those 2 methyls, right? So just be careful. That numbering is really important. Number those atoms, right? Number those atoms. So that gets us here. And somebody should have, oh my gosh, look at, what does that look like to you all? That looks like a tetrahedral intermediate, doesn't it? Do you have any good leaving groups? No? So let's just do protonation then. So the last step will just be protonation. So the difficulty here isn't the mechanism part. You gotta know something about like which one side you choose and why, based on sterics. It's really the numbering. That's what people goof up, is the numbering more often than not. They'll lose a carbon along the way. 6, 5, 4, 1, 2, 3. There's your product. Under basic conditions, you get that. Now, somebody has some really good questions about epoxides. Why are epoxides reactive? Right? Why are ethers aren't reactive? Right? If I showed you this, right? An epoxide is just an ether in a 3-membered ring. And this is an ether. This ether's not that reactive. Why is this reactive? It all comes back down to hybridization states and bond angles, actually. What's the hybridization state of this carbon? Does it have any pi bonds? It's sp3 hybridized. What's the bond angle for an sp3 hybridized atom? 109.5, right? I'm no geometry wizard, but does that look like, right? Does that look like 109.5 there? Was that like about 60 if it's an equilateral triangle? Thank you, Mr. Blismer, geometry class. All right. That's going to be really strained, right? That's going to have a lot of ring strains. That's going to make this bond much more reactive than you'd expect because the orbitals can't overlap that well, right? Just because the bond angles are goofed up. So that's why epoxides are much more reactive. What would happen, a couple people ask this, what if I have an epoxide that looks like this? That's equally substituted on either side. Then what happens? Then there's no selectivity anymore, right? Darn it. Then you don't have selectivity. Then acidic or basic conditions, you get both products, right? So only for these unsymmetrical, right? Unsymmetrical meaning the carbons of the epoxides have different substitution, can you get differences in regioselectivity products with acidic or basic conditions, right? So if it's something symmetrical, it's gonna be tough to differentiate between those two carbons. Get one or the other.